Hello, I'm Ian and I'm back with a new crash course, this time on the topic of chemical bonding. So let us begin. Chemical bonds are the binding forces of attraction between particles, which can be atoms, ions or molecules, and which result in a lower energy arrangement. The formation of a bond involves the redistribution of the outer or valence electrons of the atoms concerned. So one way to depict it is through such a diagram. For example, if two hydrogen atoms were infinitely far apart, right, their energy is defined at this point as zero. And as the two atoms actually come together, a bond is formed and the system becomes more energetically stable, and thus the potential energy decreases. But when the atoms come too close to each other, they repel each other, causing the potential energy to increase once more. The internuclear distance, which is the distance between the two hydrogen atoms, where there is a lowest energy, potential energy, is the ideal bond length, or we can call it the equilibrium bond length. Another way to depict bond formation would be the use of pushing arrow diagrams, which I'm sure all of you will be very familiar with when you study organic chemistry. So in this case, the acceptance of a proton by the OH minus hydroxide anion is represented by a double-headed arrow of a lone pair on the oxygen atom moving to the H plus cation, right? And because this distribution of electron density from residing solely on the oxygen atom to being shared between the oxygen atom and the hydrogen atom leads to the formation of a hydrogen-oxygen bond. So the key idea behind chemical bonding is that negatively charged electrons are attracted by positively charged nuclei. And we also note that different nuclei attract the valence electrons to different extent. And this can be described by electronegativity trend, where electronegativity is the relative tendency of an atom in a covalent bond to attract the shared electron pair. So electronegativity increases from the bottom left hand side of the periodic table to the top right hand side of the periodic table, right? And electronegativity trends are best explained in the context of atomic structure, and I will not be going through in this video today. So what we have to understand about ionic and covalent bonds is that fundamentally they are just two ends of a spectrum that many can consider to be fairly continuous. On one end is the covalent side of the spectrum, when the electronegativity difference between the two atoms is zero. For example, for homonuclear diatomic molecules where the two atoms are from the same element, then the bonding electrons are more stable when held equidistant from each atom, attracted equally by each nucleus. And the bond energy is the energy stabilization achieved by the attraction between the electrons, the shared electrons, pair of electrons, and the two nuclei of the atoms. On the other end of the spectrum is an ionic bond, whereby there's no sharing of the pair of electrons, but the pair of electrons involved in bond formation relies solely on the more electronegative atom, thus forming a cation and an anion, right? The anion being the atom which now gain the pair of electrons. However, there's somewhere in the middle where it is where bonds are polar covalent. That means the electrons prefer to lie closer to the more electronegative atom, but it's still shared and it's not completely residing on the more electronegative atom. So that the less electronegative atom incurs a partial positive charge, and the more electronegative atom incurs a partial negative charge. Let us now take a look at ionic bonding and Fajan's rule. So a pure ionic bond can be modeled as attraction between two opposite point charges. However, in reality, many bonds have slight covalent character. That means the electron pair is not entirely on one atom. A bond between two ions have greater partial covalent character when the cation is small and highly charged, and the anion is sufficiently large. So let us take a look at what Fajan's rule says. Fajan's rule says that the cation that is small and highly charged, thus have high positive charge density and is more able to pull the electrons from the large electron cloud of the anion to itself, sharing in with some of the electrons. And remember, the covalent bond is characterized by electron sharing, and so this sharing in of the electron causes the ionic bond to possess a certain degree of covalent character. We thus say that the cation has high polarizing power, the anion is readily polarizable, and there is significant electron sharing resulting in partial covalent character. So when we move from sodium chloride to aluminium chloride, what we observe is that the anion remains the same, but the polarizing power of the cation increases because the cation becomes more highly charged and also smaller in size. As a result, the covalent character increases from sodium chloride to aluminium chloride, so much so that aluminium chloride exists as simple covalent molecules and no longer as an ionic lattice. As we move from aluminium fluoride to aluminium bromide, on the other hand, we note that the polarizing power of the cation remains the same now in this case, right? Because the cation is the same, but the anion becomes larger and larger in size as we add more electronic shells. Thus, the ease of polarizability of the anion increases. There's greater polarization of the electron cloud, greater sharing of electrons, and thus greater covalent character. It is thus no surprise to us when you learn that aluminium fluoride is an ionic compound, but aluminium chloride and aluminium bromide are covalent. So from now on, we will mostly be discussing covalent molecules. Let us take a look at how to draw Lewis structures for covalent molecules. So normally, the central atom is the less electronegative atom, or we can say that the central atom is the atom which can form the most number of bonds, right? Next, we determine the number of valence electrons of each atom and determine the number of bonds each atom needs to form to achieve octet, considering also the possibility of dative bond formation. Next, draw possible Lewis structures or dot and cross diagrams trying to fulfill the octet rule for each atom. And normally the best Lewis structure, the actual Lewis structure of the particular compound is one where the octet rule is fulfilled and there's a minimization of formal charges. So let us take a look, however, at a few interesting cases where there are exceptions to the octet rule. So the first exception to the octet rule is that molecules that have less than 8 electrons in the valence shell of an atom, for example, boron trichloride and aluminium chloride. So this often results in special chemical reactivity for such compounds. So for example, for boron in BCl3, boron only has 3 valence electrons. Thus, there is no way it can form an octet because it can only form 3 covalent bonds with chlorine atoms. Same for AlCl3. However, this means that the boron atom in BCl3 has the possibility of fulfilling the octet rule by accepting a lone pair of electrons through the formation of a dative bond with another atom which has a spare, which has a lone pair of electrons that it can donate to form the dative bond. Thus, it can react with such molecules, for example, ammonia, to form an adduct. The second case is molecules with unpaired electrons in the valence shell of the atom. These molecules are also called radicals. Note that molecules with an odd number of total valence electrons must be radicals because there's no way to arrange all of the electrons in bond pairs and lone pairs. There must be one unpaired electron left. And the third example is molecules with more than 8 electrons in the valence shell of an atom, and this is also called hypervalency. So let us take a look at hypervalent molecules for a moment. Hypervalent molecules are molecules with more than 8 electrons in the valence shell of an atom. It is only possible for elements in period 3 and beyond as they have vacant and energetically low-lying orbitals available for the expansion of the octet. So what do I mean? Let us take a look at PCl5. So PCl5 is a case where the central atom, which is a phosphorus atom, has an expanded octet. Like, just count. There's 10 valence electrons about the phosphorus atom, which is greater than the expected 8 if octet rule were to have hold. And so this is quite puzzling because we observe that from the electronic configuration of phosphorus, which is 3s2 3p3, phosphorus should only form 3 bonds and thus have an octet of electron, of electron or valence electrons. So how does phosphorus then be able to form 5 bonds? This is because it can promote 1 electron from the 3s orbital to a vacant and energetically low-lying 3d orbital. So why is this possible? Because the 3d orbitals are of the same quantum shell as the 3s orbital, and thus it does not require a lot of energy to promote the electron from 3s to 3d, and the energy stabilization achieved by the formation of 2 additional bonds actually compensates for the slight energy increase caused by this promotion. So now let us take a look at VSEPR. Right, VSEPR is a theory that is used to predict the shapes of the molecule based on its electronic structure. So the principle behind VSEPR is actually very easy, and in fact there was an A-level question being asked before on what are the principles of VSEPR theory. So the VSEPR theory's central tenet is that electron pairs, bond pairs and lone pairs around the central atom of a molecule are arranged as far apart as possible in space to minimize their mutual repulsion. So steps to deducing molecular geometry using VSEPR are as follows. Firstly, draw the dot and cross Lewis structure of the molecule including the lone pairs. Count the number of regions of electron density around the central atom. Note that a lone pair is one region of electron density. A single bond is also one region of electron density. A double bond, a triple bond, they are all one region of electron density. Because the double bond and the triple bond, they are all pointing in one direction in space, right? So the pi bond and the sigma bond of the double bond is pointing in the same direction of space. So that's why we consider it acting as one region of electron density. So let us take a look at the geometry of certain molecules with different number of regions of electron density. So when there are 2 regions of electron density, to minimize repulsion, the 2 regions of electron density will result in a linear electronic geometry, and the molecular geometry would thus be linear. When there are 3 regions of electron density, the electronic geometry will arrange itself in a trigonal planar arrangement. So the 3 regions of electron density will arrange as if they are the 3 vertices of a triangle in a single plane. So the molecular geometry, if there are no lone pairs, will be trigonal planar. But the molecular geometry, if there's one lone pair, will be bent, because we are acting as if the lone pair is invisible, but the lone pair is still exerting the repulsion on the other 2 regions of electron density. So what do we see? We observe a bent geometry. When there's 4 regions of electron density, the regions of electron density arrange themselves in the tetrahedral geometry, where the regions of electron density act as if they are vertices of a regular tetrahedron. When there are 0 lone pairs, the molecular geometry will be tetrahedral. 1 lone pair, the molecular geometry will be trigonal pyramidal. 2 lone pairs, the molecular geometry will actually be just bent. When there's 5 regions of electron density, the regions of electron density will arrange themselves in a trigonal bipyramidal electronic geometry. Right, so you can imagine these 3 regions of electron density form a triangular base, and then there are 2 vertices, one on top and one below, 2 apexes, one on top and one below. So when there is 0 lone pairs, the molecular geometry will simply be trigonal bipyramidal. And note that lone pairs are more stable when held in the equatorial position. Right, I will not prove this in this video, but you can easily prove it by just considering the distance between the regions of electron densities from one another. And when there's 1 lone pair, the molecular geometry will be seesaw in shape. Like, imagine this is the base of the seesaw and this is the 2 ends of the seesaw. When there are 2 lone pairs, it will be T-shaped, and when there's 3 lone pairs, the molecule will simply be linear. When there's 6 regions of electron density, the electronic geometry will be octahedral in nature. That means the regions of electron density will arrange themselves to form the vertices of a regular octahedron. So when there are no lone pairs, the molecular geometry is octahedral. one lone pair, it will be square pyramidal, and you can prove that all of the positions of the octahedral electronic geometry, they're identical. So it doesn't matter where you put the lone pair, right? One lone pair, no matter where you put it, the geometry will still be square pyramidal. Two lone pairs, the molecular geometry will be square planar, right? Because the two lone pairs are arranged themselves such that they are opposite each other. So if all regions of electron density are equivalent in terms of the amount of repulsion it exerts to the others, the following will be the bond angles in the structures, right? 120 degrees for trigonal planar, 109.5 degrees for tetrahedral, and so on and so forth. However, we note that there's a second tenet of VSEPR theory, which is that lone pair repulsion is greater than lone pair-bond pair repulsion, which is greater than bond pair repulsion. For example, when there is one lone pair, the lone pair will repel the bond pairs to such an extent that the angle between the bond pairs, which is the bond angle, will be less than that were all the regions of electron density identical in their repulsive effect. If there are two lone pairs, then it will repel the bond pairs such that the bond angle will be even smaller. So this general rule of thumb is that each lone pair reduces the bond angle by around 2.5 degrees. So let us take a look at another correction that we must make to VSEPR theory, which is the effect of electronegativity of the central atom. Note that NH3, PH3 and ASH3 have the exact same electronic and molecular geometry, right? Having one lone pair and three bond pairs about the central group 15 atom. However, we do observe that there's significant difference in the bond angle, with the bond angle being highest for NH3 and lowest for ASH3. Now, how do we make sense of this trend? We make sense of it as such that N is more electronegative than P, drawing its bond pair in NH3 closer to itself compared to P drawing its bond pair in PH3 to itself. The bond pair electrons are thus closer to the central atom in NH3 and exert more repulsion. Let me show you a drawing so that you can visualize this. So for the nitrogen atom in the NH3 molecule, the bond pairs of electrons are held close to the central N atom since N is highly electronegative. The bond pairs thus exert more repulsion against each other, widening the bond angle. However, for PH3, the bond pair of electrons lie further away from the central phosphorus atom because phosphorus is less electronegative. And thus, you realize that the bond pairs are now exert less repulsion on one another, and the bond angle decreases to a smaller value. Now let us take a look at an orbital perspective of bonding. Right, the picture of valence bonding thus far has been discussion of electrons as discrete particles or as very vague terms such as regions of electron density. However, we know that electrons occupy orbitals which have distinct shapes in 3D space. You can consider covalent bonding as when the valence orbitals of the two atoms forming the bond overlap. The two orbitals are either both singly occupied with an electron, or one is filled with a pair of electrons and the other is an empty orbital, and this represents dative bonding. So let us first take a look at sigma bonding. A sigma bond is formed when two orbitals overlap head-on. A sigma bond can be formed from an overlap of one s orbital and another s orbital. It can be formed from the head-on overlap of an s orbital and a p orbital, and it can be formed from a head-on overlap of two p orbitals. And that's all you will learn in the H2 syllabus. A pi bond, on the other hand, is formed when two orbitals overlap side to side. So note that a pi bond is weaker than a sigma bond because side-to-side overlap in a pi bond has a smaller degree of overlap than the head-to-head overlap in a sigma bond. A double bond consists of a sigma bond and a pi bond. So the idea behind the formation of a double bond is to form two bonds in the same direction. So the way to do that is to have a head-on overlap, and we can't have a second head-on overlap in the same direction, right? So we have a side-to-side overlap of two p orbitals. A triple bond consists of the formation of one sigma bond and two pi bonds which are 90 degrees to each other. So let us take a look at the next concept, which closely links to the formation of single bond, double bond, and triple bonds, which is hybridisation. So let us apply the idea of orbitals to analyze the bond formation in methane, CH4. So carbon in its ground state has this electronic configuration 1s2, 2s2, 2p2, and the 1s electrons do not participate in bonding because it is an inner shell. Instead, only the valence shell electrons participate in bonding. However, as the 2s electrons are already paired, there are only 2 electrons available for bond formation, and this suggests that carbon forms 2 covalent bonds. But we know that carbon forms 4 bonds in methane, and in fact in most organic compounds. We thus must make use of all 4 valence electrons of carbon somehow. So let me propose, why not we promote an electron from the 2s subshell, 2s orbital, to an orbital in the 2p subshell. Does this work? Yeah, certainly it may work, because the 2s orbital and the 2p orbital, they are in the same valence shell, same quantum shell. So there's not much energy that is required, only a small amount of energy is required for this promotion, which will be outweighed by the fact that carbon can now form 2 stabilizing covalent bonds additionally. However, there's a problem with this. We do know that the p orbitals, they are 90 degrees to one another. So this suggests that carbon form 3 bonds 90 degrees to each other using its 2p orbitals, and 1 bond that sticks somewhere else using its 2s orbital, right? Just somewhere else, because the 2s orbital has spherical symmetry anyways. But we know that in CH4, the bond angles are 109.5 degrees and the bonds are arranged in a tetrahedral arrangement, right? That means the 4 orbitals used for bonding must be equivalent. And so we combine the 2s and 2p orbitals to form 4 equivalent orbitals, and we call this 2sp3, right? 2 for the quantum shell, the electronic shell, n equals to 2, and sp3 because it is formed from the mixing of 1s orbital and 3p orbitals. So now we form 4 equivalent orbitals, allows for the formation of 4 equivalent bonds that we know methane has. This process of combining the orbitals is called hybridisation, the term applied to the mixing of atomic orbitals, or if you want, the superposition of atomic orbitals in an atom to generate a set of equivalent orbitals. And we know from mathematical calculations that the 4 sp3 orbitals form a tetrahedral shape, nicely agreeing with both VSEPR theory and our experimental observations. What about ethene? What is the hybridization like in ethene? So we note that ethene must definitely reserve an unhybridized p orbital per carbon atom to form the pi bond, because we learned that pi bonds in our H2 syllabus can only be formed between 2 p orbitals overlapping side to side. And we know that each carbon atom then forms 3 equivalent sigma bonds 120 degrees apart, thus necessitating the use of 3 equivalent orbitals. So the answer will be an sp2 hybridization. We reserve a 2p orbital for the pi bond, and we mix the remaining s and p orbitals together to form 3 sp2 orbitals. And the 3 sp2 orbitals form a trigonal planar shape, as we know from calculations, agreeing with VSEPR theory and experimental observation that ethene is a planar molecule with the HCH bond angle being 120 degrees. What about ethyne? Ethyne is this molecule over here, where there's a CC triple bond. Now we need to reserve 2 p orbitals on each carbon atom to form 2 pi bonds. And then each carbon atom then forms 2 equivalent sigma bonds. The hybridization that works here would be to reserve 2 2p orbitals and combine the remaining 2s and 2p orbitals to form sp hybridized orbitals. The 2 sp hybridized orbitals form a linear shape, agreeing with VSEPR theory, which tells us that ethyne is a linear molecule. This marks the end of section 1 of chemical bonding. Stay tuned for the next video of chemical bonding. Thank you.